Susan, yours is embargoed? Fancy.
Yeah, I'm still working on it.
Oh. Okay. Thanks for that little bit slow ramp up this morning, afternoon, whatever time of day it is. Now we're going to talk about nonlinear relationships. Dun, dun, dun. Oh, that's a whole wall of text. Just hang on, stick with me. We'll be okay. Nonlinear. What is linear? You might be saying. Linear regression is everything we've done so far. Both additive models and interaction models or multiplicative models, like this one. You're used to seeing this, B0, B1, X1, B2, X2, maybe B1, 2, X1, 2. All of those have been linear models because we're fitting lines, straight lines. The prediction equation always results in a straight line between that describes the relation between the predictors and the DV. What is going on? Oh. So it's the conditional or expected y at each value of x, and those are always on a straight line. And a 1 unit increase in x1 results in a constant increase in y regardless of where you are on that distribution, like this. We had talked about how sort of in a straight linear relationship, you pick a value of x and you can get an expected value of y. In a non-interactive model, the slope is constant, so you can say the slope is always 1 here. But in an interactive model, you still have to pick a value of x and there's always a value of y. And in every model you make, it's a straight line. Now this is an example of a nonlinear relationship or an exponential relationship. Exponents, do you know that word? Exponent? Stick with me, it's going to come back. With exponential change, the predicted line is not straight. So it's going to continue to increase as y increases, meaning the rate of change or the size of the slope is dependent on the value of x where you look. So the relationship of x with y depends on the value of x. Here the value is pretty weak. The relationship is pretty weak when x is low, and when x is high, that slope is much stronger. Here's another example of a non-linear relationship. This is not linear, but it's a quadratic function. With a quadratic function, y is sort of leveling off as x increases. So here at the low end, it's a strong relationship. And then as x goes up, the relationship gets weaker. So the rate of change between 0 and 1, that slope, is different than the rate of change between, say, 7 and 8 or 6 and 7. So why would you look at something like this? You might have research questions that are exponential in nature. As a fake example, the number of ounces of beer consumed and how productive I am when I'm writing. For the first about 12 ounces of beer that I drink, my productivity goes up. It's a strong, positive relationship. Eventually, that acceleration slows down and stabilizes. And if I were to continue to drink beer, it would turn negative. You will see, for example, if you keep going up this way, it's like, oh, I'm writing so fast. I'm doing so good. This is not helping. And then eventually it's really not helping. And then I would keep going and it would come all the way down here. It would be really bad. Oh, somebody said something snarky, I bet, and I can't see it. Stupid chat.
Oh, I said it was the bomber speak.
Wait, oh no, I didn't hear you.
The bomber peak. Isn't that what it's called when it just increases and then it decreases?
I don't
For
know.
writing, I think that's what it's called.
I didn't know that. That's awesome. Bomber?
Yeah, BALLMER.
Oh, I have heard of that. Yeah. I think you're right. I think I saw it on XKCD. That's where this example came from. So now, here's an actual example that's not just made up for silliness. In 1967, Janus, he thought that he could get people to engage in healthy behaviors through fear, but only to a point. If people are too afraid, the result is sort of denial of existence of the threat and people continuing to do the bad behaviors and sort of ignoring it and pretending it's not real. I don't know what that's like. Or have you heard of the Yerkes-Dodson curve? That is, I can't believe that's not my example. That is, it looks almost exactly like that. It's stress and productivity. It looks like this. As stress goes up, a little bit of stress is good. A little bit of stress and you're like, no stress, and you're sitting on your couch watching Netflix, because what else are you going to do with your day? And then as stress goes up, you start to go, okay, I guess I have to do my assignments for class. And then you're actually working. But then if stress keeps going up, then you're back in your blanket fort on your couch because you're just too stressed out to do anything anymore. I talk about this a lot at my house, the Yerkes-Dodson curve. That's a nonlinear relationship. So if you think a relationship like this exists in your data, maybe it's only part of this curve, just this piece, or maybe it's only this part of the curve or some other pieces of it. Just, it doesn't have to be the whole curve. But if you think a relationship like that exists in your data theoretically, how do you test for it? The key of how you test for it is in those words you already know, exponential and quadratic. You make a new variable again, and the new variable is the interaction of the first variable with itself. Oh, what? It's an exponential variable. A quadratic variable, x squared. And so then your regression equation looks like it did with an interaction. It's b0 times b1 times whatever your first variable is, and b2 times your new variable, which is x squared. An interaction with itself. Ah. Just to sort of give you a peek into what the data looks like here, you have the regression procedure, which thinks it's analyzing a line, a linear relationship, but it's not because you're tricking it, because the data don't know where they come from, which is why you're the one with the ethics training, not the data. So if your variable 1 was 8, your variable 1 squared is 64. If it was 15, it's now 225. That's it. I'm just squaring numbers. Does that make sense? This is your original, this is your original data. This is your new data. So we do multiple linear regression with the variables, and the program is just, you just are tricking it. And I'll show you what it looks like. So what I have here in some fake data that I've made up is I have y, which is the number of questions somebody gets right on a quiz out of 20. And then variable 1 is amount of time spent practicing in minutes. It's like a memory test or something where you could actually feasibly get better with more time practicing. My kid today was like singing a song about 100 digits of pi, for example. If you're trying to practice and learn the digits of pi and you spend 2 minutes, you're going to get 5 of them, 3.14159. I knew the next one. That's all I know. So then as you increase the amount of time you're spending practicing, people look like, I'm eyeballing, they look like they're getting better. But it also looks like they're then not getting as much better as you keep spending more time practicing. You get to 15, and then you keep practicing, but you're not getting that much better, and you keep practicing, and you're not getting that much better. And so the research question that I want to ask here is, does spending more time practicing result in better test scores? And does that relation change with more time spent practicing? Or is there a nonlinear or quadratic relationship between amount of time spent practicing and the number of questions or number of digits they get right? So all I've done is run that regression equation just like we talked about before. It looks just like your linear regression, but I'm putting in my first variable, which is my linear, and this one, which is that variable squared. So number of minutes spent practicing and number of minutes squared. And so what you'll see here is we have, yes, our linear term is significant, and yes, our quadratic term is significant. Our linear term is positive, so that means when both of these are 0, my slope is going to be positive. Does this look positive to you? Am I mirrored? Does that make, like, if my box is a y-axis, is that the y-axis? Is this
You're
the
mirrored.
Oh man, how am I mirrored for you and not for me? I'm really glad I asked. That makes a lot of sense.
There's a way of changing that in your video settings, but don't ask.
Yeah, don't ask me how. Okay, so then this is your y-axis and this is your x-axis. Does that look right? Could you hear that? I'm sorry, I got away from my mic. Okay, here's y, here's x. So at 0, when variable 1, when my minutes are 0, and the other one is going to be 0 too because it's just squared, I've got a positive relationship. Going from 0 to 1, I'm increasing by 3 digits. It's positive. But then, as this keeps going up, that negative 1.38 that I'm pointing at, you can't tell I'm pointing at it, this negative 1.38 means that slope is getting less steep as that number gets higher. So it's like, it's going to get, you can't see that at all, can you? It's going to get less steep as you go up. That's what that negative 1.38 means. And now I will actually walk through that on the slides. Oh, fancy. I forgot I did this. When you spend 0 minutes practicing, you're going to get negative 1.9 questions right. Now, this is a 2052 Olympics problem. This is just conjecture beyond our actual data. We don't have anybody who studied 0 minutes in this data set. Here's how you interpret the main effect of this first variable, which is time spent practicing. When variable 1 is 0, an additional minute of time spent practicing, we expect to see 3 more questions right, 3.5 more questions right. The interaction term here tells us that there is a significant nonlinear effect of time on studying, such that the relation decreases as time increases. This is really, if your research question is the relationship a linear one or not, this tests that null hypothesis right here. Yes, there is a significant nonlinear relationship. Now, just like with interactions, the meaning of the coefficient changes when you include the interaction of the variable with itself. And to demonstrate, I have the results of this table both ways. I have the results of this equation with just the linear relationship and then one with the linear and the quadratic. So you can see how it changes. Look at how much weaker this slope looks. 1.557 when you don't account for the quadratic effect. Isn't that wild? So we're used to this. This is normal. When you spend 0 minutes practicing, you get 3 questions right. And here it's when you spend 0 minutes practicing, you get negative 1.9 questions right. Because of the extrapolation. Now here, for every minute spent increasing, or every minute increase in time practicing, you're getting about 1.5 more questions right. Whereas here you have to put it in space, just like with interactions. That slope is only valid at that point when your x is 0. Dun, dun, dun. And these equations work just like your other equations have worked in the past. So our y hat is equal to negative 1.9 plus 3.5 times x minus 1.38 times x squared. And so if you want to figure out and solve this equation for any particular value of x, you just plug it in here and here. So if it's 0, obviously it's 0, 1, 0. If it's 1, it's 1. And 1 squared is 1, so that's boring. If it was 5 minutes spent practicing, it would be 5 and 25. So you can see how this little tiny, it's not very big, but it can make a huge difference when you're multiplying it by 25. It's really going to decrease the size of that slope. So I've plotted it here using the equation. I made this sort of this plot of the line of best fit. And this, what this interaction variable here represents is how fast the curve is changing, basically. What you're getting here is the line that's tangential to the curve, just to like get all mathy on you for a second. Do y'all remember tangents? Like that. It's the line at this exact point. I guess it has to be 2 points right next to each other here. So this line is tangential to this curve. That has a slope of 3.5. But as you go up, it's not as steep. The line that's tangential to this curve is not as steep anymore. And all the way up here, it's almost 0. Whoop, doo, doo. That's really fun. So it's getting less steep as your x value gets higher. And you can think about it like an interaction because you would talk about it just like any other interaction. The relationship between x and y depends on x. That's why it's an interaction with itself. Before we've said the relation between x and y depends on another x variable, like an x2. Here, it's just itself. I think I'm just saying everything I've already said. Here's our B0. This is the interpretation of B1. I called it the simple slope because do you remember we talked about the simple slopes when you can plug things in to your model? So this is the slope when x equals 0. This is describing how the slope is changing. You might say the curve is showing deceleration. You don't have to say that. You can just say that it changes. So to bring all of that together, in this instance, what we would say is that the relation between the outcome and the predictor is not linear, and it shows some deceleration as the value of x increases, where the relation of x with y depends on x, And at higher levels of x, the slope is weaker. Drawing parallels again to the other pieces that you've learned. In our original regressions, the question we ask is x related to y? And then we look at the b value, and that answers our question. And if that b value is significantly different from 0, then we reject the null hypothesis, and there is a relation between x and y. When we did this with multiple regression, it's the same thing, but with multiple variables. With an interaction term, we were asking, does the relationship of x with y depend on x2? And if the interaction term is significantly different from 0, then we say that there is sufficient evidence to reject the null hypothesis, and the relation of x with y is dependent on x2. And so just like those, with the nonlinear sorts of models, we allow for the possibility that this might be what it looks like. We might see a nonlinear relationship. And the extent to which that interaction term is significant, that tests the null hypothesis that it is or is not consistent across that distribution of x.
Dr. Logan,
Mm-hmm.
is it possible that, okay, so when you have just the independent variable that you're like just the variable that you're considering as like a predictor, can that be non-significant and then its interaction with itself be significant? Is that ever possible?
Oh, yeah.
Okay.
What would that look like?
It would just be flat and then maybe decreasing or increasing
Yeah, where would it be flat?
in the beginning.
Uh-huh.
And then it would
Get a better marker.
I don't know, I'm trying to draw it. Would it be like this? The last one?
Yeah. Uh-huh.
Yeah.
Because the line, so I did it this way. The line that's
Okay.
tangential to that curve, so if this
Yeah.
is 0 point,
Yeah.
it's at its tangent here, when it's 0,
Mhm.
that's a
Yeah.
flat slope.
Right.
That relationship is 0.
Right.
But once you allow it to interact with itself,
It
the
increases.
yeah, it will.
It can also decrease, right? It can also go the other way. It
It
can
should.
become.
Yep. It could also go the other way.
Yeah.
Exactly. Now,
Okay.
I don't know if that answers your question, which was your question, could it look like 0 in the main effect before you include the interaction?
Yeah, like I mean, if the variable by itself doesn't have a strong relationship with what you're trying to predict, but then you put in the interaction term and it is, like, how do you interpret that?
Let's look at, we're actually basically done with this section, so this is the fun part. If you have, oh, I don't have that here. If you have a relationship, sorry. If you have this sort of Yerkes-Dodson
Yeah.
relationship,
Mm-hmm.
on average,
Mm-hmm.
if you didn't allow for the interaction,
Mm-hmm.
the slope would probably be 0.
Right. Yeah, because you're taking the center of the graph into consideration.
You're not allowing the slope to vary. So with
Right.
this one, wait, am I
Mhm.
still sharing?
Yes.
Yes, okay. With this guy here,
Yeah.
when we ignored that relationship, it's just
Mhm.
not very strong, 1.5.
Right.
And you
Mhm.
can see that that's because you would overestimate, you would have like not do a good job at this end, you'd overestimate
Mhm.
everybody. And
Right.
here you would underestimate everybody in
Right.
order to get a line that fit this really well.
Yes. Yeah.
Now, you
Mhm.
can imagine that if this continued and went on down this way,
That. Yeah.
that the slope, it would look like there was no relationship.
Right. Yeah.
If this
Yeah.
was mirrored here and you could
Yeah.
draw, if you looked at the line of best fit, in order to
Yeah.
best fit all of those points, it would have to overestimate here,
And
underestimate
underestimate
here,
on that
and then
side. Yeah.
overestimate here again.
Right, when it rises again.
Mm-hmm.
Okay, yeah.
And so in something like that, it would look like there's no relationship,
There's nothing, yeah.
even though there
Yeah, because
actually
you're
is one.
taking a part of the data that just looks like that.
Wait, say that again.
You're saying you're taking a part of the data that just seems to look like that.
You might have data that you
Right.
think looks like that.
Got it. Okay, yeah.
And
But
so
you need to extrapolate it to figure that out.
you would, well, if you, so this, in this theory, the theory here behind this relationship
Right.
is that some stress is good, but too much stress is
It's
bad.
bad, yeah.
And so in
Mhm.
order to test that theoretical relationship, you have to allow that to vary across levels of itself.
Right. Yeah. Understood.
I'd love to have actual data on that. I don't have any.
Dr. Logan?
Uh-huh. Yeah, go
I
ahead,
have-
Jamie.
Um, does testing for a non-linear relationship, does that help against like type 2 error? I mean, because in the short term, it might look like you don't have a relationship, and so you fail to reject the null. But then if you extrapolate it out and there is a relationship, I don't know. I'm just wondering if that's ever done to see if there is indeed, if you've committed a type 2 error.
Hmm.
That's a good question. I've never seen it phrased that way. But you could make that argument that you would want to look for it. I have seen in some literatures, in developmental literature, people will covary out age and age squared. So they want to control for both of those things because age can have a linear effect on longitudinal outcomes, and it can have a nonlinear effect on longitudinal outcomes, because things like imagine any child that you've ever met. I'm trying to come up with these graphs. A kid who's learning language, if you've ever known a 2-year-old, it's like they learn 5 new words every single day. And then eventually we're not learning 5 words every single day anymore. That's a very, not at all. So that's a very simplified relationship, but that's one of the reasons why they would put age squared in the model, because they're not interested in this developmental trajectory. They're interested in what's informing the developmental trajectory.
Mhm.
So they'd control for those things and look at other pieces of the other things that might relate to it. So I haven't seen anyone say, I'm going to look at whether this is related linearly or non-linearly just in case.
Yeah, I don't know if that gets into like data mining territory or whatever, but I just was curious.
You might actually be committing a type 1 error, meaning you would find this relationship even though a relationship does not exist, because you're playing with the data more and more. So one of my topics that I want us to get into is actually about that. So to talk about what does it mean to continue to poke at your data, asking these hypothesis tests over and over and over again of your data, because you really hit an important topic there, Jamie, about type 1 and type 2 errors, because you're, on the one hand, maybe there's a relationship that exists here if you just were to control for the relation of X with itself. On the other hand, just testing for something because maybe it's there, after you test it one way and then trying it a different way, it violates the assumptions of the hypothesis tests that you're looking at. Because the goal of your hypothesis testing, remember, where we have a 0.05 rejection, a 20%, like we're okay with 20% of the time we would see a result this extreme or more extreme if there's not really a relationship here. That's what our p-value represents. And if you then run 20 tests, if you remember from probability and rolling dice one after the other, you can absolutely, what happens is that then you end up making those type 1 errors, and you're going to find things that are there just by chance. Sorry, I didn't intend to lecture about that today, so I apologize. I'll pull something together that's actually coherent on that for our last week. And then Jamie, I didn't mean to cut you off there. Did I answer your question?
Yeah, thanks so much.
Okay. So the last thing that I want you to do on this topic is I want you to spend a couple of minutes thinking about the data you've used for your homework assignments and that you've used for your final project. And think about a research question that you could look at with nonlinearity. And to draft that research question now. So I have 2 examples of what this might look like. And Shantanu, this one is more similar to the one you suggested, where the relationship is 0 at the low end and then gets stronger as you go up. This is also a valid nonlinear relationship, as is its cousin, its opposite cousin. This one, where there's a relationship at the low end and a relationship at the high end and not in the middle. So I'm going to stop talking and let you think about your data. What I want you to do is draft a research question. Does one of these make more sense than the other? And if so, label it. Just draw a quick and dirty plot on your scrap paper. And I'm going to put 10 minutes on the clock for you to do this. Don't worry, I'll pull that back up. Oh, come on. Can you see that up here? I got a volunteer. All right, Shantanu.
So I was actually studying collective efficacy in my data, and I actually found that democratic classroom practices sort of mediate the relationship between collective efficacy and capability. But I wanted to see if the level of autonomy you grant to students sort of interacts with itself and leads capability to decrease as you leave them to, how do I explain it? Leave them to their own devices way too much. I actually put the regression into into SPSS just to see if it did and to verify, and it doesn't. Autonomy is great.
Okay, but so we went too far. So back up. What do you think that relationship looked like? Was it one of these or was it something different?
I thought it would be the first one that we discussed. So the one with the bomber peak, it rises and then it stops. So the second one, I'd say, like and then you mirror it.
So
on the
you're,
other side. Yeah.
and then it would just it would go on
Yeah.
back down
Yeah.
again. So you
Yeah.
were thinking that this was
Yeah, this was
autonomy?
democratic pedagogy, and that was capability. So democratic pedagogy is like where you let everybody become an equal agent in their education. So it means they have higher autonomy support. So I
Okay.
thought increasing democratic pedagogies would first increase capability because everybody likes autonomy. But then as they were sort of left to their own devices more, it would decrease it because they have no assistance.
Yes. One of my girlfriends was just telling me about a class that she took in
Mhm.
grad school where the professor put them in groups and said, you have to figure out what the problem is that you're trying to solve. And then they didn't come back
Mhm.
till the end of the class, like the entire class, like
Right.
several weeks. It's like, that's very independent. So the more democratic pedagogy goes up,
Yeah.
the
First
weaker the
capability would-
slope gets.
Yeah, it would increase and become steep. Then it would sort of decline after some time.
And
And
what's
the
this outcome is self-efficacy,
capability.
capability, self-ratings of capability.
Yes, but like this is a computer-supported classroom, so it's more the comfort associated with using tools to flourish and learn.
Oh, cool. Is it weird for you taking an online class?
Me? No, I love it.
It's a little weird for me hearing that you study the kind of work that I'm trying to learn how to do right now, which is teach well online. Self comfort.
Yeah, let's say capability.
Oh, capability. All right, so that was the idea. As democratic pedagogy goes up, you're thinking that that relationship is going to decrease.
Yeah, or just capability, not self-capability.
Oh,
Sorry, my bad.
that's
Cool.
I wrote it wrong. Okay, that makes sense. Thank you. Who said next? Hannah? You lost your
Hi.
pup. Oh
He's
no,
here.
there she
What are you
is.
talking about?
Okay, good.
Loyal companion. I was thinking the same scale. I'm looking at grades, the final grades, and a course that teaches students information literacy. And then I'm also looking at like the student year ranking. And from the start, even before I knew that this was a way to be looking at the data, I was like, well, the further a student gets along in their career, the more their final grades should be higher and just basically leveling out. But the freshmen should really see a jump between freshman and sophomore. But the juniors or fourth years and fifth years, whatever, really should be leveled out and about the same. They should have the same grasp on both the information literacy skills we're teaching as well as some of the digital literacy skills.
Got it. So this is the difference between a freshman. It's the association between how
Student year and the student final grade in the course.
right. So it's like saying the difference between freshman and sophomore is bigger than the difference
Yep.
between sophomores and juniors, which is still bigger than the difference between juniors and seniors.
Yep, and I'm just counting them as like a single year rather than semesters or course like hours taken.
Yeah. I like that example. That makes a lot of sense. Also. Okay, Michelle, do you want to go also?
Sure. So I've changed my research question. Now I'm actually looking at students' procrastination in an introductory physics class. And we actually have a real-time measure of when the assignment was posted online to when they actually turned it in. So I actually have their time in minutes as a measure of their procrastination and their final grade in the course. And then we also have their self-reports of procrastination as another measure to compare. But for this purpose, I just did the actual time in minutes. And I would guess it would look like the stress curve, where to a point it would be better and then it would go down after a certain point.
So people who, the difference between 0 minutes and 1 minute That's it's probably not fast enough, but maybe it's too fast. 0 hours and 1 hour. It's a strong relationship between. Oh no, wait. What's the outcome? The outcome is the grade in the course. Is that right?
Yeah.
So let's.
And then
I know that you think it's going to go the other way also, so we'll pretend that it's going to keep going. I actually think I can edit this. Nice. And while I do that, see if you can write a sentence about the difference between the slope here and the slope here, like I did for the freshmen to sophomores. No?
I've got, yeah, so I'll do it in days, even though my data's in minutes, it's easier. So they had 6 days to do the assignment. So I would say something like the difference between the scores for the students between day 1 and day 3 would increase strongly, probably level off between day 3 and day 4 and start going back down at days 5 through 6 as they get closer to the due date.
Whoa. Okay. So you're saying that people who are spending too little time in between assignment and completing the assignment are going to have a low grade in the course, and people who are spending a lot of time are also going to have a low grade in the course. But people who are spending an average amount of time are going to have a better grade in the course.
Maybe it's more of a negative going all the way down and not that inverted.
Like this one here, too little time, or more like this one?
Well, more like starting at the 15 and then going down. So that half of it. So that
Okay.
yeah. So if they're doing their homework early, they should get a high grade, and that will level off as they go down and get closer to the due date.
Kind of like that.
Yes.
Come on. Okay. So like this. So as they're spending, if they're doing it pretty quickly, those are the students who are getting a good grade in the course. And the longer they're waiting to turn it in, the worse they're going to do in the course. But the relationship here is you could spend an hour or 2 hours or 3 hours, and that's still within the margin of error of students who are going to be doing a good job. But it's those students who are waiting 4, 5, 6 hours or longer. They're just going to keep getting worse and worse and worse.
Right.
Cool. I like how different those are. Okay. That's all I have on nonlinear relationships. Play with them if you want to. You can do that in lab this week. You will learn how. You will not have an assignment where I explicitly ask you to try this out, but if you would like to do that, you can turn that in as an optional homework, and I'll look at it for you if you would like me to. But that's all. I just want you to have the concepts and understand how it works in your own data and head. So anything else on that before we look at peer review?
Yeah, Dr. Logan, would you always use regression to look at nonlinear relationships? Like, is this the standard kind of analysis for doing that? If that makes sense.
Mm-hmm. Yes, unless your outcome is dichotomous, in which case you're looking at a logistic regression. But yes, regression is this course is being replaced in the catalog next year by a course called General Linear Modeling. And that's because general linear modeling is the umbrella that holds all of regression and ANOVA. So it's like what I was describing, it's sort of all the same thing. We're all in this together. So yes, I would always use regression to do something like this, unless I'm in some sort of other modeling framework like structural equation modeling, but the principles are all sort of the same. We allow something to covary or interact with itself in order to look at whether the relationship changes across the distribution of itself.
Thank you.
Yeah. Okay. So for next week, you will be doing some peer reviews. Before I have you doing peer reviews, I want you to know that I have a couple of resources and readings in Carmen for what to think about during peer review. Now, they are comprehensive for when you're actually doing manuscript reviews as like for journals. So I want to show you within that. So this one is called How to Write a Peer Review. There's a nice section called Before and After Sample Reviewer Comments, where they have some comments like, I don't understand what you're talking about. And instead, they give you some suggestions of how to be more specific and constructive with your feedback. So I recommend that you read this. Like, please don't say the writing is so bad, it's unreadable. That's not a constructive piece of information. But saying the language is unclear and it makes it difficult to follow, that's much more informative and helpful. So that's what I want you to really pay attention to. There's also, it continues, there's a couple of pages of this stuff. And then within this one, it's terribly formatted, but I really liked the overall message of being a constructive reviewer and what that looks like. And just for fun, I will tell you about one of my most favorite things. Come here. Hello. This is called Your Paper Sucks. And it is a compendium of real life reviewer comments that have been submitted to people, to us. So people will get terrible reviews and then send them in. And just if you'd like some nice Schadenfreude and a way to brighten up an afternoon and some good non-examples, have a look through this little guy. Not useful. This is a confusing paper. I can't finish reading this paper, and I certainly will not recommend it to anyone else. Just so mean. Don't be mean. Today, a reviewer asked me to explain a correlation coefficient. So enjoy. They didn't, well, oh, that's so mean. So it's here, and it's also on, it's on the tumblers. If you have a preferred format of looking through things, you can find them. I'm sorry about this, reviewer. If you'd like, I can get you a new one. Woohoo! That's good. That's a good one. We never get those. So if you get, do we need to clarify the meaning of all? They make me laugh. Okay, so I pointed this out to you in order to say that this is a really good example of what not to do. And also, please enjoy It's very fun when you need some time to just sit back and laugh a little bit. Okay, so good examples of reviews and some good non-examples of reviews. And then the last thing I have for you is that I'm having you review 2 peers. And then you'll spend all of class in your little pod next time. If you know someone that you would very much like to work with, please email me your pod requests. I spent a good chunk of the day trying to figure out how to put together some sort of survey so you could like pick people anonymously and send them to me, and I just couldn't figure it out. So instead, we're going with the old-fashioned method of chat with each other. If you want to be in a pod together, let me know. If you know, like, oh man, I worked with Krista last week and that was really helpful for me, she's awesome, you can email me and say, I really loved working with Krista, I'd love to be in a group with her. And I will do my best to make everybody's group dreams come true. If I don't hear from you by like noon tomorrow, I will go through and randomly pick people for you. Yeah, because Krista's always helpful. Okay, so send me your requests, your nominations, and that's all for today. And I'll stick around for a couple of minutes, but otherwise, have a week as best you can. Maybe read some more of that blog. We're ending a little early today.
So I did check, and to change your video settings, it's actually really simple. You just do the caret next to video, and it has video settings, and you can mirror it, or you can touch up your appearance or low light.